Hi everybody, welcome back. Today we're going to be working on polar coordinates. Now, what I want to start off by saying with polar coordinates is that polar coordinates rely solely on trigonometry. We must be able to take this x and y coordinate system, in other words this Cartesian coordinate system, and we must be able to convert it into polar coordinates. Now, every single point in the Cartesian coordinate system will be able to be mapped to one specific point in polar coordinates. Now, what I have here on the screen for the first picture here, I have drawn an angle theta and a point on some grid. Point P is going to be denoted as r comma theta. In other words, it has two different inputs. It has a radii, which is r, and it has some angle measurement theta. And the angle measurement will always be measured from the positive x-axis. But under polar coordinates, we don't call it the positive x-axis. We just call it the polar axis. The origin in Cartesian coordinates is the ordered pair 0, 0. In polar coordinates, we do not call it the origin. Instead, we call it the pole. Now, aside from that, we can also talk about finding a polar coordinate in terms of r theta. What would happen if we get a negative radius? Now, going back into trig, we know that r is given by the square root of x squared plus y squared, and we'll get to that in a bit. But in that sense, r can't really be negative. However, if you go back to trig, when we started looking at r, we also started dissecting vectors. A vector cannot have a negative length, but it can have an opposite direction. And that's kind of where r comes into play. Not necessarily theta. Theta does have something to do with it, and I'll explain that in a bit. But if we're ever given an r value that's negative, we just take this point and reflect it oppositely. In other words, we change its direction. So starting from the origin, if we were going in this direction, following my mouse all the way to this point, that's the original direction. Changing its opposite direction, or changing its direction to be opposite, we just start here, and instead of going in this direction, we move backwards in this direction. This point here can be thought of as the point P, which is negative r comma theta. If we don't want a negative value for the r, we can interpret it as r, and then we just take our theta, and this is what's changing the direction here, and all we're going to do is add pi to it. In other words, 180 degrees. So we have different ways of interpreting these negative radii when we're talking about polar coordinates. Now, let's get into a little bit more details and a little bit more specification. So what I'm going to do here is I'm going to get a grid started. That way we can start illustrating what polar coordinates do when we look at the Cartesian coordinate system. There we are. Alright, so this is my y and this is my x. I'm going to identify a random point here on the screen. Let's say this is point xy. Alright, that means that if I go downward here, this is a value of x, and that means if I go horizontally here, then I'm over at y. However, that's not what I really want to focus on. What I really want to focus on is what is the distance? What is the distance here from the origin to that specific point? Well, that distance we're just going to label as r, and if we use the distance formula for this, we naturally get that r is equal to the square root of x squared plus y squared, as such. I don't like the way that looks. I cannot guarantee it. X squared plus y squared. There we are. Now, how do we then interpret this from the Cartesian over to polar coordinates? Well, one of the things that we have here that we made when we selected this point was that we made some angle theta. Now going back to trig, we have this right triangle taking place here, and we can start extracting. We can say that cosine of theta is going to be equal to x divided by r, and we can also say that sine of theta is going to be y over r. Now, if this is the case, we can go ahead and we can solve for the x-coordinate. The x-coordinate in this particular case, if we multiply by r, it's just r cosine of theta. If we multiply by r in this case, then we get that y is equal to r times sine of theta. Now, in trig, we arrived at this conclusion using the unit circle, where a unit circle would have a radius of 1. Now, if that's the case, then naturally all of the ordered pairs, x and y, would just be cosine theta, sine theta, and we'd be done. Alright, so this is one thing that we do have, and this is our bridge. This is how we go from Cartesian over to polar coordinates, and vice versa. This is where we go from polar coordinates over to the Cartesian coordinates. Alright, so we do have a bridge that we like to work with. Now, another aspect that I like to work with here is tangent of theta. Tangent of theta is the same tangent that we looked at, which is just y over x. Awesome. So let's identify a little bit more differences between Cartesian and polar coordinates. Alright, so here I have these this grid here, and I'm just going to identify some of the differences for the Cartesian coordinate system and for the polar coordinate system. Alright, so on the Cartesian coordinate system, we have an x and y axis. Under the polar coordinate, we do not have an x and y axis. All we have is a all we have is a polar axis. And this is just the positive x-axis. Now, we're going to see how this works once I get into the illustrations through Geogebra as to why we only have one of these axes. Alright, so far so good. Cartesian, we have x and y, but in polar we have our polar axis. All of the ordered pairs in Cartesian coordinate system look like xy pairs. All of the pairs in polar coordinates look like r comma theta. In the Cartesian, we have what is known as your origin, which is ordered pair 0, 0. In polar, we just have a pole, which, again, we classify just as a point 0, 0. Alright, so we do have some differences here that we can start looking at when we're starting to look at Cartesian and polar form. Alright, now in polar form we do have the polar axis, but we also have what are known as concentric circles. And I'll elaborate more on that in just a little bit. So in Cartesian we typically have a rectangular grid. In polar form we have a circular grid. Alright, now if we can think of more aspects, or we can think of more differences, and we'll go ahead and we'll jot them down. But at this particular time, these are the only ones that really come to mind just by looking at my notes for what I have here. Alright, so it's going to be important for us to identify what's happening here, Cartesian and polar, and we want to make sure we use that terminology. Alright, so let's go ahead and let's start looking at what the polar grid looks like. So for that, I'm going to take you over to Geogebra. Alright, so follow me along and we'll get started in a bit. Alright, so I'm here on Geogebra, and again, I just went on to geogebra.org, and I went here down to where it says Geogebra Classic, and I clicked on that, so I'm right here. Now, Geogebra Classic by default automatically goes to the Cartesian coordinate system. In other words, the rectangular coordinate system. And in here we can see our x-axis, we can see our y-axis, and we see the rectangular grid. However, if we have the option, or if we have the luxury here, we can actually change this and we can make it into polar coordinates. And that's what I'm going to do here. I'm going to change this grid over to polar coordinates, and this is what it looks like. Alright, now I'm going to modify this because when I change it on Geogebra, it doesn't exactly give me everything that I need. So what I'm going to do is I'm going to stop showing the y-axis here, and I'm only going to show the positive numbers for that y-axis. There we are. Same thing for the x-axis. I'm only going to show these positive numbers. There we are. Now I want you to look at this grid right here. This grid is made for the from this polar axis right in here. Its pole, it's right smack in the middle, and all of these concentric circles, look at that, they are representative of radii. So this first circle here has a radius of 1, second circle has a radius of 2, third circle has a radius of 3, fourth circle has a radius of 4. You also see these vertical lines, sorry, not vertical, slanted lines. These slanted lines are representative of angle measurements. So its polar axis here is an angle of 0, or going all the way around, 2 pi. The first angle that we see here should be an angle measurement that is going to be between 0 and pi halves. This would probably be fitting of 30 degrees. This angle here would probably be fitting of 60 degrees. And we can keep going in that manner. Therefore, if we try to identify some random point in this regular Cartesian coordinate grid, well, we can also identify that point using polar coordinates. Well, how would we identify this point A in this particular case? Well, we would say, you know what, we went out to a radii of 6, so its radii is 6, and it falls exactly on the angle measurement of pi thirds, which is 60 degrees. Therefore, this ordered pair has a coordinate of 6, which is r, comma, pi thirds, which is 60 degrees. In other words, your theta. So, we're going to be able to identify any given point Cartesian into polar coordinates. Alright, and that's just by using this layout right in here. So let's go back and let's go ahead and start working on this. Alright, so here we are. Now what we're going to do in this particular case is we're going to go ahead and work on this example. And this example is going to say that we want to plot the points whose polar coordinates are given. And then we want to find the Cartesian coordinates of that point. So if you look on the screen here, I went ahead and I just took a small screenshot of the Geogebra polar coordinate grid. Now what I did here is I elaborated a little bit more, and I said, hey, every single one of these slanted lines represents an angle measurement. This first one, the polar axis, is 0, in other words 2 pi, and then after that we're just going to be increasing by 15 degrees. 15 degrees, or we can think about it as pi 12s. So pi 12s, pi 6, pi 4ths, pi thirds, 5 pi 12s, and then pi halves. Now I'm going to go through and I'm going to identify my point here. So my first point, which is 4, comma 4 pi thirds. So I'm going to go over to radii of 4, so radii 1, 2, 3, 4, and then I'm going to go to 4 pi thirds. Alright, 4 pi thirds, that means every pi thirds is 60 degrees, so that means I went 60 degrees here, and then I went another 60 degrees. Alright, so I went another 60 degrees, and then I went another 60 degrees, that puts me at pi, and then I went another 60 degrees, which should put me at about 240, so that should put me about right in here. Make sure that is the, nope, there we are. Perfect. So this ordered pair here is 4 comma 4 pi thirds, just like such. All right, let's look at the next one. The next ordered pair we want is -2 and 3 pi fourths. So -2 and 3 pi fourths. So what I'm going to do here in this particular case, because my radii is negative, I'm going to plot the positive version first, and then I'll reflect it 180 degrees. So I'm going to go out to a radii of 2, and then I'm going to go to 3 pi fourths. 3 pi fourths just means that we moved 3 times by 45 degrees. So my first 45 degrees should be here, 45 degrees. Second 45 degrees should be here. And then third 45 degrees should be right here. Now, that's not my final point, because this point is 2 comma 3 pi fourths. We want it to be negative. So all we do is just reflect it 180 degrees to this point. This point is now -2 and 3 pi fourths. There we are. All right. Now, could we have done it differently? Yes, we could have done it differently. We could have thought of this as a radius of 2 and then an angle measurement of -45 degrees, and it would have been the exact same. All right. So this, again, could have had 2 comma -pi fourths, and it still would have been the same answer. And there's going to be a lot more answers to just this particular piece, all right, to this particular point. There could be 2, 3, 4, 5. There could be an infinite amount of different values that we can have that still make us land on that exact same point, which is a little bit different from when we were working with Cartesian coordinates. Now, let's look at the next one. The next one's going to be -3. So we're going to be, again, I'm going to do this positive radii. So 1, 2, 3. All right, now I'm going to go to -pi thirds. -pi thirds just means I traverse in a negative direction for my angle measurement. So I'm going to go down to -pi thirds. So that's going to be -60 degrees. Keep going, keep going, keep going, and it's right in here. So my initial point of 3 comma -pi thirds is here, but I want it to be negative for my radii. So all I do is I reflect it 180 degrees to here. This ordered pair is -3 comma -pi thirds. So there we are. We have those 3 points identified on here. Now, could we find a different ordered pair that would land us in the same spot? Sure. We could have made this here just a radii of 3, so radii of 3, and then just traverse all the way here, which would have been 2 pi thirds. In other words, 2 times those 60 degrees. That would have been our same angle measurement for that exact same point for part C. All right, so now that we can see that we can develop more and more points, let's go back and let's finish answering the question. Because the question said, find the Cartesian coordinates of those points. So I'm going to be working with part A first. Part A says I have 4 comma 4 pi thirds, like such. And again, by what's given to me, they're saying that these are in polar coordinates, so this means I'm given some r and some theta. So I know by extraction I have that r is equal to 4, theta is equal to 4 pi thirds. There we are, as such. Now all I need to do is I need to extract what is x and what is y. In order to do that, what I'm going to do is I'm going to use my bridge, that x is equal to r times cosine theta, and y is equal to r times sine of theta. Since that's the case, I'm able to extract my x coordinate, which is just going to be 4 times cosine of 4 pi thirds. My y coordinate, which will be 4 times sine of 4 pi thirds. So all I need to do now is go ahead and figure out what is 4 pi thirds. All right, so we're going to go through it, and we're going to have my x coordinate here. So 4 pi thirds, you can think of pi thirds. Pi thirds is really 60 degrees. Cosine of 60 degrees should be 1/2. but 4 pi thirds is in quadrant 3, and cosine is negative in quadrant 3. So really, this is just 4 times negative 1/2. That would make this sine of 4 pi thirds, since it's in quadrant 3, that sign would be negative, so it'd be negative root 3 over 2. Because again, we have that they are co-functions of one another. In other words, co-angles of one another, so they just alternate by 90 degrees. Now that we have this, we can extract that x is negative 2 and y is negative 2 root 3. Which means under the Cartesian coordinate system, my ordered pair should be negative 2 root 3. And there's your answer for part A. The ordered pair that satisfies this polar coordinate is negative 2 comma negative 2 3 root 3. Awesome. So let's work on the second one. Let's work on part B then. Alright, so let's work on part B, and I'm going to do the work down below over here. So part B, we're going to be looking at the ordered pair of negative 2 comma 3 pi fourths. As such, again, I'm going to extract what I am given. I'm given my r and I'm given my theta, so r is equal to negative 2, theta is equal to 3 pi fourths. And again, I want to extract my x and y coordinates, so that's negative 2 times cosine of 3 pi fourths. Y is negative 2 times sine of 3 pi fourths. So as we keep going with this coordinate system here, so that's going to be negative 2 cosine of 3 pi fourths. 3 pi fourths should be in the second quadrant. Cosine is negative in that second quadrant, and pi fourths should just be root 2 over 2, so this is negative root 2 over 2. Sine of 3 pi fourths should just be the complement of that, so that's going to be quadrant 2, that's positive, so it's just 1/2. Not bad. Or excuse me, not 1/2, just root 2 over 2. There we are. So that means our coordinates, x and y coordinates, that's going to be root 2, comma, this piece here, which is going to be negative root 2. Alright, so now we have to then look at this. Alright, so we're going to go over here and we're going to start looking at this. This coordinate in polar coordinates landed here. If we superimpose the x and y coordinate system on this polar grid, this point would be in quadrant 4. So the point that we get here is this point in quadrant 4. Yes, positive x, negative y, which means it's in quadrant 4. Awesome. So you always want to go through and double check. If you've plotted your polar point and you've converted that polar point into Cartesian, go through and double check. Does it land in the same quadrant that you initially put in polar coordinates? If it does, great. If it does not, my suggestion is check your trig. Oftentimes, the answer is going to be in there. Alright, here we go. R is equal to negative 3. Theta is negative pi thirds, which once again, we want an x coordinate. The x coordinate is going to be negative 3 multiplied by cosine of negative pi thirds. Y is going to be negative 3 times sine of negative pi thirds. Alright, here we go. Cosine is an even function, which means this is really just negative 3 times cosine of pi thirds. And cosine of pi thirds, that's just cosine of 60 degrees. So that's going to be 1/2. There we are. And again, it was positive, so I don't need to worry about that negative. Now, when we look at the y-coordinate, sine is an odd function, which means negative times a negative, so this is just going to be 3 times sine of pi thirds. It's the co-function of 1/2, so this should just be root 3 over 2. Alright, which means our x-coordinate here is negative 3/2. Y-coordinate is root 3 over 2. Now let's check. This coordinate under Cartesian coordinates is the coordinate that is in quadrant 2. Let's look at the point, -3, -pi3. -3, -pi3 falls in quadrant 2, again, if we were to superimpose the Cartesian coordinate system onto this polar grid. So it still stands to reason that we're still ending in the same quadrants as we're viewing this in polar coordinates. Alright, now that's really good. Now what we're going to do next is we're going to take what we know about graphing these polar coordinates or graphing these specific points, and what we're going to do is we're going to start graphing these polar functions. Alright, so we'll come back in a bit. Alright, now there is one more item that I wanted to add up here. Remember I said that if we had more to add, we'd come back to it? There's one more thing that I wanted to add here. Typically in the Cartesian, we have some functions that we look at in terms of x. And this is just typically y. Under polar form, we are going to have functions, but the functions are going to be based off of some angle measurement or this independent variable that we will call theta. So whatever radii we get or whatever radii we're looking for will be given by that theta measurement. Alright, now this is only for functions. We can still graph equations and we can still look at equations both in Cartesian and polar, and we can still generate those specific graphs. Alright, so before we start graphing some of these equations, I want to go through and I want to give you a brief rundown of tips and tricks to try to graph these equations a little bit more easily. Alright, now one of the first things that we want to look at when we're talking about symmetry and trying to make things a little bit more easier for us is going to be here. Alright, we're going to have a symmetry about the x-axis. If the point r theta lies on the graph, then the point r comma negative theta will also be on the graph. Alright, now symmetry about the y-axis, same thing's occurring, except the point is going to be negative r negative theta that is going to exist on the graph if it has symmetry about the y-axis. If it has symmetry about the origin, then the point r theta and the point negative r theta will also be on that graph. Now let's look at how that looks like visually and in polar form. So I'm going to go to Geogebra really quick to show you that visualization. Alright, now here we are on Geogebra. This is my page in Geogebra, so if you want to search for me on Geogebra, you can. I have a page set up there that I do a lot of different animations or applets or different functions that I like to graph and give you illustrations for. Now what I'm going to do is I'm going to start off with the symmetry about the x-axis, and that's going to be this middle one right here. So looking at this symmetry about the x-axis, I want you to notice the symmetry here. Right? We're still considering that this is going to have symmetry along the polar axes. Alright, so if any given point, and let me stop this point here, any given point, say point A here is going to be r comma, let's say negative theta, then the point negative r, if this point A is point r theta, then this point here must be r negative theta, which means same radii, except it went in a negative direction. And we can see it right here, right? Here is, it looks like it's about a half, so a radii of about a half. And then the angle measurement here went all the way up to, looks like pi thirds, which means the other opposite direction, it came in negative pi thirds. So this is what it looks like to be symmetric about the x-axis. If we can get symmetry for polar graphs, then that means we don't have to go through all of the different angle measurements. That means we could just go through about half the angle measurements, and then since we know it will have symmetry, we can just go ahead and reflect it across the respective axis or origin. All right? So that's with the symmetry about the x-axis. Let's look at the symmetry about the y-axis. Looking at this symmetry about the y-axis, notice I have this one point, call it point A. This will be, let's say, r comma theta. This other point over here, I'm going to call this point negative r negative theta. Well, negative r negative theta. So negative theta, that means it went down negative theta direction, stopped, and then to get a negative radius, we reflect it across to get this point here. So naturally, whenever we have reflection or whenever we have symmetry across the y-axis, it's going to look like this for these specific graphs. And again, I just animated these little line segments to show you that as you start traversing, the line segments will mirror each other across the axis that they have symmetry on. So this is symmetry along the y-axis. And again, we're going to be looking for different types of symmetry within the respective questions or the respective graphs that we're looking for. Let's look at one more. We're now going to look at odd symmetry. So here we're going to have odd symmetry, or sorry, I said odd symmetry. Here we're going to have symmetry about the origin. So symmetry about the origin, if we have my initial point here, let's say my initial point was A over here, which was r comma theta, then that means symmetry about the origin must have a point at negative r comma theta. So if we go to the same radii, same theta, and then make that radii negative, that means we're reflected across the origin, it would get us to this point here. Now again, if we start showing the animation here, this is what symmetry about the origin looks like. It looks kind of like you took the reflection for the x-axis and then the reflection for the y-axis, and you were able to get the first quadrant and the third quadrant in order to get those reflections going. So this is what we're looking for when we're talking about symmetry with respect to the x-axis or about the y-axis or about the origin. This is how it visually looks. All right. So now that we have a little bit more tools at our disposal, let's go back and then let's start defining a few more things. All right, so here we go. Now what I'm going to do here is I'm going to start off with an example, and I'm going to want to sketch this curve, which is r is equal to 1 minus cosine of theta. All right, so this is one of the first curves that I want to sketch. Now, naturally, you can also think about this. Remember, the radii or the radius here is some function of theta, which means the radius is dependent on whatever theta is, like such. So we can write it in this manner if we would like. All right, whichever manner you would perform to do it in, by all means, that's going to be a perfect way. All right, so we're going to go through really quickly and we're going to check some of this symmetry. All right, and we're going to check some of the symmetry to see what's going to occur and then how we're going to go about it. All right, so here's one of the first things that I want to check then. I want to check, in this particular case, r is equal to 1 minus cosine of negative theta. All right, so what I'm doing is I'm inserting a negative value for theta. So I'm inserting a negative value for theta. That means I'm checking for symmetry about the x-axis or the y-axis, simply because I'm either going to be looking for this to occur or this to occur here. All right. Now, there is one thing that we know about cosine. Cosine is an even function, which means cosine of negative theta is the same thing as just cosine of theta. All right, and this was because cosine is an even function. Now, since that's the case, we naturally just get the original equation back, which means the original r value doesn't change at all. So what does that tell us then? That then tells us that r of theta is going to produce the exact same result as r of negative theta. Oops, excuse me. are of negative theta. All right. Now, what does this tell us then? Well, what kind of symmetry will that then produce? If one of the points is going to be r theta, and naturally the other point is going to be r negative theta, that means we have symmetry about the x-axis. All right. So that's one way to work it. Nice. So now, if we start looking to see how we can possibly get this one here, now notice, because I substituted negative theta, I didn't get a negative r. If I were to be able to factor out the negative from both of these terms in my original equation, then my r value would be negative. Since that is not the case, I cannot have symmetry about the y-axis in this particular case. All right, so now that we have found symmetry for the y-axis, symmetry about the x-axis. All right, so perfect. I just found symmetry about the x-axis, and again, we can go through the whole process and saying, hey, symmetry about the y-axis doesn't happen, symmetry about the origin, doesn't look like we're going to have symmetry about the origin as well. So all we're going to have to do now is we're going to have to go through some of these curves, and we're going to see how, we're going to have to go through some of these points in order to generate the curve. That way we can get a good picture of this graph. All right, so now one of the things I want to check here is looking at 1 minus cosine theta, or looking at this function here. What is the period for that function? All right, so that's one thing I'm looking for in this particular case, is what is the period? So what is the period for 1 minus cosine of theta? Question mark. So to answer this, we then have to go back to trig. Well, trig tells us that if we're graphing 1 minus cosine theta, then one period, because theta is not being multiplied by any specific number other than 1, this is going to have a period of 2 pi. So one period is 2 pi. And the reason I say that one period is 2 pi and why we want to focus on this, well, because when we have to graph this, we know that we have symmetry along the x-axis, which means I only need to graph one part of the x-axis, or one part of this function with respect to the x-axis. I either graph the top part of this function and then reflect it, or I graph the bottom part and then reflect that. So one of the items that I then want to do is then I want to say, okay, well, let's only graph from, let's say, 0 to pi. And again, 0 to pi because that's only half of the period. So what I'm going to do now is I'm just going to start picking random points from 0 to 2 pi, enough of these points to get me a good picture for what's happening here with this function. All right, so let's try to start picking some of these points. All right, one of them is going to be theta, the other one's going to be f of theta. Whoops. Sometimes when I grab the ruler on the screen, it doesn't shift over. It's kind of annoying, but hey, we do what we have to. There we are. All right, perfect. So I want to go through some values to start seeing what's going to occur. All right, naturally the first one is going to be 0, so I'm going to choose 0 here. So when we substitute in 0 into our function, so cosine of 0 should be 1, so 1 minus 1 is going to get me 0. All right, and again, what I did was I substituted in cosine of 0. All right, next one. The next one, what we could do is we could go to, let's say, pi 6, in other words, 30 degrees. So when we substitute in pi 6, that's 1 minus cosine at pi 6. All All right, that's 30 degrees. Cosine at 30 degrees should be root 3 over 2. So this is going to be 1 minus root 3 over 2. So I'm going to say this is 1 minus root 3 over 2. All right, looking good. Now 1 minus root 3 divided by 2. This should get me an approximation. I'm going to get an approximation here of 0.13. All right, let's go to pi fourths. All right, pi fourths, substituting that in, that's 1 minus cosine at pi fourths. So that's root 2 over 2, so that's going to be 1 minus root 2 over 2. So then all we got to do here is 1 minus root 2 over 2. Let's look at that. That should get us an approximation of 0.29. All right, looking good. So now we got pi fourths. So let's now jump a little bit further. Let's go to pi halves. After we go to pi halves, we're going to go to, let's say, 3 pi fourths. And after we go to 3 pi fourths, we're going to go over to, let's say, pi. And we'll see what occurs there. Right, so here we go. Next one, pi halves. So we again substitute in pi halves, cosine at pi halves. This should get me 0 here. So cosine at pi halves should be 0, so 1 minus 0 should just get me 1. All right, looks pretty good. Let's keep going. All right, so at 3 pi fourths, we're going to substitute in that value. So that's going to be 1 minus cosine at 3 pi fourths. Cosine should be negative here, which means we should get 1 plus root 2 over 2. So if we do 1 plus root 2 over 2, we should get about 1.7 as an approximation. And then finally pi, 1 minus cosine at pi. So 1 minus cosine at pi, so cosine at pi, that's going to be negative 1. So this should be 1 minus negative 1, which naturally gets us 2. Perfect. So now that we have this, we can now go through and we can now start graphing what we need. All right, so I'm going to get a polar coordinate grid going here, and then we'll start showing the graphing in just a bit. All right, so here's I have this polar graph for polar coordinates, and what I'm going to do is I'm just going to start plotting the points, all right, that we're looking at. All right, and again, what I want to do is I want to start labeling my lines here. All right, that was 0. This one here is going to be pi fourths. All right, so there's pi fourths, and then I can have in here, this is going to be pi 6, and this one's going to be pi thirds. So let's go with the ordered pair. So I have 0, 0, so there's my first one. The next one's going to be at a radius, and remember f of theta is another word, or is another labeling for just r. So my radii here is 0.13, so 0.13, that's very, very small here at pi 6. So at pi 6, we have a really small radius, and there's our point. Now at pi fourths, we're closer to 2.29, so about 0.3. So about 0.3 is a little bit more than halfway here. Sorry, it's a little bit less than halfway. There we are. And that's at pi fourths. And next one, we're going to go to pi halves. At pi halves, we're up at 1. There we are. So pi halves, we're up at 1. At 3 pi fourths, so at 3 pi fourths, this one, that's this one here, 3 pi fourths, we're going to be at 1.7. So this here's a radius of 2, radius of 1.5, so 1.7 right smack in the middle. And then over at pi, we're going to be at 2. So we're going to go radius of 1, radius of 2, here we are. Now again, I'm only graphing the top half because again, we have symmetry. So what this graph looks like right now, looks like this. I'm trying to make it a little bit more smooth. Whoa. Yeah, not quite as smooth when you're trying to do it with a stylus, but it's okay. Whoa. Alright, so here's going to be the top half, but we know there's symmetry, and since there's symmetry, what we're going to do is we're going to reflect this part down below. So all of these points that we have here, they're just going to be reflected down below over here. So when we had a radius of 1.7 for this angle, then we're going to have a radius of 1.7 for that angle down below on the third quadrant. All right, this angle here produced a 1, and that's where we have a 1, and then these angles were kind of turning into themselves, just like this. And there we have it. This is the actual graph that we're looking at. This is a graph of 1 minus cosine of theta in polar form. Now let's go check on GeoGebra, make sure we got this correct. Alright, so I'm here on GeoGebra, and I'm going to go through and I'm going to see if I got this correct. So I want this 1 minus, and we said that was cosine. So that's going to be cosine of theta. There we are. Hit enter on that. Perfect. Look at that. It's the same graph that we found. Same graph that we found, and again, we're able to then see the symmetry here a little bit more clear, right? If we were to draw that x-axis here, it cuts it directly in half. So this here looks almost like a heart, right? So almost looks like a heart. Now, typically, we call these cardioids. This is a picture of a cardioid, specifically because, again, it looks like this heart-shaped figure. All right, so 1 minus cosine, awesome. That's all done and in the books. All right, so the graph, wow, my writing is horrendous right now. So the graph, this one down here, is called a cardioid. All right, so here we have a cardioid. Nice. So let's try a different example now. All right, let's try this example here. Let me see, where did I start there? All right. So here goes the next example. We want to sketch the curve of r is equal to 1 plus 2 cosine of theta. All right, and we're going to see what this gets us. All right, we could go through symmetry first, so let's go through some of that symmetry. All right, so here we go. We want to sketch this curve. R is equal to 1 plus 2 cosine of theta. Now, when we want to sketch this, again, we can take the exact same approach that we did up here, and that's exactly where I want to start. I want to start by identifying any type of symmetry that we could possibly have. So, let's go through and let's start identifying. Let's start looking at 1 plus 2 times cosine of negative theta and see what happens here. Alright, so 1 plus 2 cosine of negative theta. Now again, cosine is this even function, which means we're just left with 1 plus 2 times cosine of theta. So we get the actual cosine right back, or the actual function right back, which means at this point in time, this again is going to have symmetry across the x-axis. So we have again symmetry along the x-axis. Nice. Alright, so let me identify my period, that way I can go through and once I know that I have that symmetry, then I can just look at certain parts of my period here. So symmetry along the x-axis, I have that period, so let's see, period is 2 pi, and again, because theta, or this input value, is not being multiplied or divided by any value. It's just 1, so my period must be 2 pi. Now, since my period is 2 pi, I'm only going to consider half of that period. So what I'm going to do is, again, I'm going to create this table so that I can start looking at these values. Now, actually, I said I'm going to create the table, but I'm actually not going to create the table. I'm actually going to do something else. This is what I'm going to do really quick. I'm going to say consider graphing y is equal to 1 plus 2 cosine of x. So consider graphing this function instead. Alright, again, I'm still looking for my period just to be from 0 to pi. So that's not going to change. Alright, there we are. So this one here is going to be, let's say, pi halves, and this one here is just going to be pi. And we can go further if you'd like to 3 pi halves, but again, we don't need to. Let's erase all that x's. I don't need it. So that was x, and that was y. And this is going to be, let's say, we'll go back here. And let's make this a 2 and this a 4. There we are. All right, and those are the y values. Perfect. All right, so let's go through. As I'm looking for my sine, or sorry, for my cosine function here, so I'm going to be looking to graph this one. So I'm going to need to remember everything I did back in trig to try to figure out how to graph this here. All right, so cosine is being multiplied by 2. That means what we're going to be doing is changing its amplitude. So the amplitude is going to be modified by 2. So instead of cosine starting at 1, we actually start at 2. And what this 1 does right here, this 1 is actually going to move, or it's actually going to shift my function up by 1 unit. So my graph for 1 plus 2 cosine x starts at 2 here, and then at the next increment, at pi halves, it starts coming downward. Oh, excuse me, I said 2. It actually starts at 3. My apologies. Starts at 3, and it starts going downward. All right, so at the first increment, we must be down at the x-axis, and at pi, we must be down below. All right, so what I'm going to do is I'm going to reflect this, I'm going to reflect that it goes down below. Whoa. Alright, so let's reflect here. Let's make sure it goes down a little bit more. So that's 1, 2, 3, 4. Alright, there we go, -2. Perfect. So now as we go down, it goes down to its negative amplitude, which should be 3. So it should be right about here. There we are. So the graph looks like this. And again, if we wanted to keep going, then we can keep going. It would come up here. Actually, like such. All right, now again, I forgot that we had shifted upward. My apologies. Jeez, it's not a good day for me. There we go. My apologies. We actually had gone down just a little bit further, and at the first increment pi halves, we should have been at that 1 increment. All right. So what I'm going to do here is I'm just going to modify this really quickly here. That way we can specify this. All right. All right. So I cleaned this up a little bit, and back to where we were going. All right, so at the next increment, it's not down at 0 because, again, we shifted up by 1, so that's the part where I forgot to account for. At pi, we're supposed to be down at its minimum amplitude, but since we shifted up by 1, that should now be over at, I'm going to say this is going to be -1 here, so cosine, going to be at -1. There we are. All right, next increment, we're going to be back up here. There we are. Perfect. And so again, the only reason I want to do this is so that I can start looking at some of these values. And here are the values that I'm going to be looking at. All right, this first value here. All right, what I want to do is I want to capture this ordered pair. All right, so one of the first things that I'm going to do is I'm going to start listing some ordered pairs. That way we can see what's actually going on. All right, and I'm going to label those values in different colors. That way we can, again, more specifically identify where they're going and how they're being used. So here we go. I'm going to identify that we're going to have some x and some y. I'm going to have some x, some y. There we are. All right, some ordered pairs x and y, and those are going to be here. And what I'm going to want to do is I'm going to want to convert those into r comma thetas. All right, and once I convert them into r comma thetas, then r comma thetas is going to be the values that I'm going to be looking to graph in polar coordinate form. All right, so let's go through the first one. The first ordered pair that we looked at here was 0, 3. All right. The next ordered pair that we looked at was at pi halves. We were at 1. And the last ordered pair that we looked at was at pi. We were at -1. Now, under this assumption that we were working with here, I want you to notice that assumption that we made. The assumption that we made at the very beginning here was that theta, this theta value, was now being called x. This r value was now being called y. By that process, what we have on this side to convert all of our pairs, we now have a method. Every x coordinate or every x value is now going to be theta. So every x value here is now theta. X value is now theta. Every r value is y. So every y value that we found on these ordered pairs is now going to be r. In other words, all we're doing in this particular case is switching the x and the y's to make them into r's thetas. So my first ordered pair should just be 3, 0. My second ordered pair should just be 1, pi halves. And my last ordered pair should just be -1 and pi. Nice. So let's go start graphing this and see how this is going to turn out, to see what we actually get. All right, so I'm going to come through here and I'm going to put the grid on here. All right, let's get the grid going here, and that was under Geogebra export here. Nice. All right, so I'm going to put my graph right over here, that way we can see it. All right, nice. Actually, I'm going to off-center it a little bit. There we go. Okay. So what I'm going to do is I'm going to start going with the ordered pairs. So my first ordered pair, my graph here started at 0, 3. So my ordered pair in polar form should be 3, 0. In other words, we go out to a radii of 3, and our angle measurement is just going to be 0, so it stays right at the origin. or sorry, it stays right on the polar axis. Now my next ordered pair is going to be 1 comma pi halves. So radius of 1 at pi halves, here we are. All right, not looking too bad. And then the next ordered pair is -1 comma pi. So -1 comma pi, again, what we're going to do is we're going to make sure that we treat this in a positive, the r value in a positive direction, and then once we find the point that we're at, we're just going to reflect it 180 degrees. So 1 comma pi, so I'm going to go out to a radius of 1, and I'm going to go over to pi, but then -1 is going to reflect it back over here. So here's what I have, that I start here at the orange point and I start traversing to this point, and I somehow, some way get back to this point here. So I must be doing something over here that I need to figure out what's going on. All right, and that process of what's going on is what we're going to figure out right now. All right, now what I want you to do is I want you to start looking at this figure here. Anytime that my graph here in green crosses the x-axis, that tells us something. All right, so at this crossing and at this crossing, this here crosses the x-axis. What does that mean about the equation though? Well, about the equation, that means that y must be equal to 0, like this. All right, so if y is equal to 0 in this particular case, we're going to see that making this assumption on this side over here is going to collapse all of these angle measurements down to 0. 0 being, hey, you're just going to be down at the polar axis. All right, so we got some stuff that we now need to consider. And the stuff that we got to consider is that not only is it going to come down, is it going to cross on that polar axis, but what's going to happen as well, or what's more importantly going to happen, is that all of these radii, because again, the y values corresponded with the radii as to how we defined it here. If the y values, in other words, the r, go to 0, then that means they're all going down to the pole. So this is very, very crucial for us. What this means in polar form, every x-axis crossing means that the polar graph passes through the pole. So naturally, visually, any crossing that we see for this graph on the x-axis, that means it's going to come right back down to the pole. All right, and again, that's going to be very, very crucial for us, because now I want to see this happening here. Look at these radii. These radii, as I'm traversing here, as my x values are increasing towards pi halves, these radii, in other words, these heights, are getting smaller and smaller and smaller and smaller and smaller. So naturally, what's happening here is we're moving in this direction. All right, and we're going to keep going in this direction. So from pi halves down to this angle between pi halves and pi, so between pi halves and pi, we're actually condensing down to 0. So we're going to actually collapse it down to the pole here. Once we collapse it to the pole, look at this radii again. This radii keeps increasing till it gets to pi. So increasing till it gets to that red point. So what I'm going to do is I'm going to keep on increasing those radii just like this. And remember, we said that we only needed half of the period, and that's half of the period here. All I have to do now is reflect this graph towards the bottom. That's it. So let's look at the reflecting here. I'm going to take this piece and I'm going to reflect it. So there we go. That piece is now reflected, and I'm going to take this big old arc and I'm going to reflect that. There you go. That's your graph. Give it a direction. It was traversing in this direction. There we are. Kind of looks like a little heart with a little extra loop. All right. So this is, again, another method to graph these polar graphs. Typically, I like to use this method a little bit more versus its other method, versus the other method where we're just picking points. I find this method to be a whole lot faster. All right, typically these here are called limacons. All right, so I'm going to say the graph of this equation is called a limacon. All right, awesome. So now we're starting to get into this and we're starting to feel a little bit better with these polar graphs. So let's go on GeoGebra and make sure we got this correct. All right, here's GeoGebra and here's a curve, 1 plus 2 cosine theta. And that's exactly what we had, right? The radii was actually increasing upward, and then it came down onto itself, and then it just kept moving right along. Great. All right, so here I am on GeoGebra. This is an applet that I developed a while back. And what I'm going to do here is I'm just going to really quickly show you one of the graphs that we want to create, which is going to be negative sine, and then I'm going to want here of 5x. There we are, and I'm just going to hit enter here. All right, lower bound from 0 over to 360, and we're going to see what's going to happen here. So on the left side here I have Cartesian, on the right hand side here I have polar graphs. And what I'm going to do is I'm going to start switching the angle here, and notice as I start switching the angle, I start getting the visualization that's taking place both in Cartesian and in polar form. Now notice we didn't need to go all the way to 2 pi in order to get the whole picture. Right, we needed to go about right, oops. You have to go about right here. There we go. That's about where we get the whole picture for this particular graph. All right. Now, this has to do a lot with the period that we're working with here. All right. So when you start looking at certain functions, what you want to do is you want to then start identifying, well, what is going to be that period that you're looking for. Once you identify what period you're looking for, or if there's any type of symmetry, then you can go through and you can start generating the rest of your graph. Now, I want you to look at this nice little star figure here. So this nice little star figure here, it kind of looks like a flower. Now, typically, anything that looks like a flower like this, we call these individual loops, we call them petals. In the next section, we're going to be interested in finding the area of these petals. If we know it has 5 petals, then we can find the area of 1 and just multiply everything by 5 in order to get all of those petals, not having to integrate over the whole domain. All right, so you guys can play around with this. Again, if you go onto my webpage on GeoGebra, so if you search for me on GeoGebra, you'll find my webpage, and you will find this applet on there. This applet is the one that says Cartesian to polar. And you'll be allowed to input any function that you'd like in here, and then you'd be allowed to change your bounds. In other words, your angle measurements. Is it going to go from 0 to pi, 0 to 2 pi? What is it going to run through? All right. So this is one of the ones that I wanted to show you. Now, let's go back to the class really quick. That way we can start seeing a little bit more as to how we're going to be using calculus with this specific polar coordinates. All right, so here's how we're going to be working with this particular case. Now, remember what I said before, that anytime that we have r, we can call this f of theta. In other words, we're going to be able to define some function in terms of theta, and this is going to be for my r values. And we also said using polar coordinates, we have x is equal to r times cosine of theta, and we have y is equal to r sine of theta. Now, one of the things that we want to do is we want to do what we were working back when we were talking about parametrization in early chapter 10, that we want to be able to take this derivative or to find the slope, that way we can calculate dy dx. So our overall goal is to find this dy dx that we're going to be searching for. All right, so remember that, that's the goal. Right now, what I want to do here, I want to take this x value. Instead of r, we have r defined differently. R is actually f of theta, because it's going to have some theta involved, and it's going to be multiplied by cosine. The y values, again, r times sine of theta, but r is just f of theta multiplied by sine of theta. So what we're looking for here in this particular case is now that x is going to be defined as some function of theta that's going to be then multiplied by cosine of theta. Same thing for y, except it's going to be multiplied by sine of theta. Now, why do we care about this? Well, the reason we care about this is because when we now start talking about dy dx, in other words, the slope of the function that we're going to be trying to observe, this is really just going to be the derivative of y versus the derivative of x, but since both of these have a theta dependency, we're going to do dy d theta divided by dx d theta. Now again, what you're going to see here is that both of the thetas are going to cancel, which means we're still only going to get dy dx. So we're going to have to go through that. In order for us to get this numerator, we're going to have to differentiate y. But in order to differentiate y, we need the product rule because we have a multiplication of two functions with the same variable. So if we take the derivative here, we're going to have to do derivative of the first, which is just f prime of theta multiplied by the second function, sine of theta, plus the first function, f of theta, multiplied by the derivative of the second function, which is just cosine of theta. Wow, that's looking pretty good. Let's keep going. Denominator now. My denominator, that's dx d theta. So dx d theta, again, I'm going to have to differentiate x with respect to theta. That means taking my first derivative here, derivative of the first function, that's f prime of theta, multiplied by the second function, which is cosine of theta, plus the first function, f of theta, multiplied by the derivative, which is going to be negative sine. So I'm going to search that sine, that's going to be negative sine theta. There we are. And this is going to be how we calculate the slope. This is how we find dy dx when we use parametrization techniques in terms of thetas. Now, I want you to sit back and think about this really quickly. Does it really matter that we parameterize with respect to theta? Right, at the end of the day, the parametrization should not matter. We could have chosen a happy face instead of theta, and this still would have worked out. Granted, the notation would have been a little bit messier, but that's why we like to choose thetas, x's, y's, z's, because the notation is easier to look at and to write. So, now that we have this, there's going to be certain questions when we want to find tangent lines to horizontal or to vertical components for a certain graph. When that happens, we then need to set either this numerator or this denominator equal to 0. So, let's go ahead and let's find out. Let's take an example. So here goes this example. Find the points on r is equal to 1 minus sine of theta, where the tangent line is horizontal or vertical. All right, so we got a few things to do here. All right, we got a few things to do. And what I'm going to do is I'm going to use this particular equation here. So I'm going to use this dy dx. I'm going to say, hey, I'm looking for dy dx, and this dy dx, according to our work, should be the derivative of the function multiplied by sine of theta plus f of theta multiplied by sine of theta, or sorry, cosine of theta, my apologies, divided by f prime of theta times cosine of theta minus f of theta times sine of theta. So now, using this function that I have here, so the function that was given to me, this f of theta, is just 1 minus sine of theta. So when we take the derivative here for f prime of theta, this is now just going to be negative cosine of theta. So as I make my substitutions, f prime of theta, that's negative cosine of theta. So I'm going to say that's negative cosine of theta. And that's going to be multiplied by sine of theta plus f of theta. F of theta, that was 1 minus sine of theta, multiplied by cosine of theta. There we are. It's looking good. All right, denominator f prime. So again, f prime, that was our negative cosine of theta, multiplied by cosine of theta, minus f of theta, that 1 minus sine of theta, multiplied by sine of theta. There we are. All right, so it's looking pretty good. It's looking pretty good, I'm not gonna lie. All right, so let's go through and let's see if we can simplify anything here. All right, so if we can simplify anything, then that's going to be great. So I'm going to put an equal sign here, and let's make sure I separate my top from my bottom. All right, here we go. Nice. All right, so up over here, I'm going to have negative sine theta cosine theta. And this is going to be plus, distribute this in here, that's going to be cosine theta minus sine theta cosine theta. All right, it's looking good. Denominator, I'm going to have negative cosine squared theta, and that's then going to be minus sine of theta minus sine squared theta. All right, looks promising. Awesome. Now, I'm actually going to stop it right there in the simplification process. So in the simplification process, I'm going to stop it right there. I'm not going to simplify anymore, but instead, I'm going to go through and I'm going to figure out what the question is actually asking. The question is saying, find the points on that graph where we're going to have a tangent line that's going to be horizontal or it's going to be vertical. Now, if it's horizontal, then the slope of that line is going to be 0. All right, so I'm going to write this in green. For a horizontal slope, the numerator must be equal to 0. For a vertical tangent or a vertical slope or vertical tangent line, the denominator must be equal to 0. So we now have this slope that we now need to decompose. The numerator must be equal to 0 in order for me to find this horizontal slope that I'm going to be looking for, and the denominator needs to be 0 when I'm looking for this undefined slope. All right, so I have my work cut out for me now. I now need to know what I need to do. So let's work with the numerator being equal to 0 first. Numerator being equal to 0. We're going to work with this first. If the numerator is equal to 0, then would you agree that's just 2 sine theta cosine theta, because I combine these two terms, they're the same, plus cosine of theta is equal to 0? Nice. I like that so far. And then here I can factor out a cosine. So factoring out a cosine leaves me cosine times -2 sine of theta plus 1 is equal to 0, which then tells me that cosine of theta must equal to 0, or -2 sine of theta plus 1 must be equal to 0. And naturally this then becomes sine of theta must be equal to 1/2, right, after I isolate sine of theta. So now I need to look for the angles where this happens. So for some of the first angles, and again, I'm looking for r is equal to 1 plus sine of theta. Since the period did not change here, I'm looking for all of my answers to be on the interval from 0 to 2 pi. So let's start finding those answers. Cosine of theta. So what angle measurements give us a cosine of that angle to be 0? All right, so I can think of two different values. We get that theta is either pi halves or 3 pi halves. All right, think about cosine of 90 degrees. Cosine of 90 degrees is 0. Cosine at 3 pi halves should also be 0 as well. All right, looking pretty good so far. Now, sine of 1/2. So let's think about sine of 1/2. When does sine of 1/2 occur? All right, so sine of 1/2, since it's positive, it's only going to be in quadrants 1 or in quadrant 2. And since it's in quadrant 1 or quadrant 2, I'm now just looking for what output for some angle gives me a ratio of 1/2 for that sine ratio. All right, sine of 1/2, that's then going to be at pi 6, in other words 30 degrees. So theta is equal to pi 6, and not only is it at pi 6, because again pi 6 is only in quadrant 1, it's also going to be in quadrant 2. So pi 6 plus 2 pi 6 plus 2 pi 6, so far we're at pi halves, and then add another 2 more, then we're going to be at 5 pi 6. There we are. So when is the numerator equal to 0? Well, the numerator is equal to 0 on these specific theta values. So let's write this up really quick. The graph will have horizontal tangent lines at theta is equal to pi halves, let's say 3 pi halves, pi 6, and 5 pi 6. All right, awesome. Now there is going to be a modification. Thinking ahead, I will come back and I'll modify that in a bit. All right, so then denominator. I want my denominator to be equal to 0 now. So let's look at that. Looking at my denominator being equal to 0, so here I'm going to have negative cosine squared theta minus sine squared, minus sine theta, there we are, minus sine squared theta is equal to 0. Now, thinking back to trig, we have to go through and we have to solve this. And it's actually not too bad to try to solve this back from when we learned in trig, because I see that I have two different trig functions here, sine and sine squared. I do have cosine, but cosine to me is not going to matter too much, because what I'm going to do is I'm going to make an insertion for cosine, all right, or for negative cosine. I'm going to use this fact that I have that sine squared theta plus cosine squared theta is equal to 1. If I isolate cosine squared, then that means I have 1 minus sine squared theta. And if I multiply by a negative, that means I have sine squared theta minus 1. And that's the value that I want to insert into here for negative cosine squared. Negative cosine squared is really just sine squared theta minus 1. All right, that was that piece that we inserted. And then we still have minus sine theta minus sine squared theta is equal to 0. And the reason I want to do this is because now we can go through and we can actually start solving this a little bit easier. All right, or let's say a little better. All right, so, and I just realized I made a mistake. I apologize. I keep on dropping the ball here. When I distribute that negative in that bottom term, this becomes a plus. So we're looking at plus sine squared theta, right? Because negative times a negative right in here, which means this is a plus and this is a plus. And since that's the case, we're going to add those two. So we're going to get 2 sine squared theta minus sine of theta minus 1 being equal to 0. And now I can go through and I can factor here. So that's going to be 2 sine theta, and this is going to be sine of theta. And then here we're going to have a 1 and a 1, and we're going to need a minus sign to be on the higher part here. So I believe this should work out, and we can just double check. Sine, that's going to be 2 sine. This here is going to be negative. That's going to be positive. That's a higher sign. That's negative, negative, negative. Okay, perfect. So from here, we set both of these equal to 0, and we should get that sine of theta is equal to negative 1/2, and then sine of theta is equal to 1. So this is all we then have to do, is to figure out where are these angles happening. All right, so let's figure them out. So sine of theta being equal to 1 on the interval from 0 to pi, that's just going to be one of them, and that should just be over at pi halves. So theta is equal to pi halves. All right, so then sine of theta being equal to negative 1/2. So negative 1/2 for sine, that means sine must be in quadrants 3 and 4. And a sine ratio of 1/2 should be down at, I want to say 30 degrees. So in other words, pi 6. So pi 6 in quadrants 3 and 4 should be 7 pi 6. And it should be 11 pi 6. There we are. So now that I have these angles, now I can start seeing where we're going to have these vertical tangents. So the graph will have vertical tangent lines at theta is equal to 7 pi 6, 11 pi 6, and pi halves. Now, before we say, hey, this is the answer to the question, this is actually not the answer to the question just yet. We have done a lot of work to show what we have so far, but there is an issue here. What is that issue? How can we have two horizontal, how can we have a horizontal tangent and a vertical tangent at the exact same angle measurement? That is the issue. So we now need to alleviate that issue. We need to see what's happening here. Are we going to be producing some horizontal tangent, or are we going to be producing some vertical tangent? We don't know. So we need to investigate. All right, so I'm going to say here, cannot have a vertical and horizontal tangent for the same angle. And again, that angle being pi halves. So we now need to consider what's happening here. So we're going to use calculus to tell us what's going on. All right, so we're going to use calculus to tell us, hey, can we then identify what is happening here on this slope? So let's go through. We're going to have to use limits for that argument. So we have to use limits to find if there is a horizontal or vertical tangent. All right, so I'm going to go through and I'm going to check the limit as my theta values approach pi halves. And I want to make sure that I approach it from two different directions. All right, so we're going to approach this from two different directions. We're going to approach it from the left, and we're going to see what's going to happen here. And we're going to want to do this for the slope, dy dx. All right, so this is going to be for the limit as theta is approaching pi halves from the left. And as it's approaching pi halves from the left, my numerator, again, I'm going to write down the initial form that I looked at for my numerator, which was cosine of theta minus, and that should have been, what was that, 2? Yeah, 2 sine theta cosine theta, just like that. Divided by, that's going to be 2 sine squared theta minus sine of theta minus 1. All right. Now, if I make a direct substitution, well, direct substitution, I already know the result. All right, if I input pi halves into my numerator, what happens? Well, I should get 0. So inserting pi halves in there gets me a numerator of 0, but if I insert pi halves into my denominator, what happens? I get 0. What does this look like? Indeterminate form. And it's actually an indeterminate form that we actually like. Yay! Simply because if we have it in this indeterminate form, then what we can do is we can actually use L'Hopital's rule. So let's go through and let's try to implement L'Hopital's rule here. Now, I'm actually going to modify this just a little bit so that I can see what's really happening, so that I don't have to use a product rule here up top. So limit as theta is approaching pi halves from the negative side, the numerator, make sure I have my dividend, or my denominator, my division sign here. So cosine of theta minus, this is really just sine of 2 theta. That's my double angle. And this here's just 2 sine squared theta minus sine theta minus 1. All right, so nothing special there. All right, and I'm going to use L'Hopital's rule here. So I'm going to say here I'm using L'Hopital's rule. And again, you have to show that you are using L'Hopital's rule. Somehow, some way, you must say you're using it. So here's my limit again. Again, pay attention to how we write the limits. We don't just drop the limits, we keep writing them as we're taking this. Apply L'Hopital's rule. Derivative for cosine is negative sine. So that's negative sine theta. Derivative for negative sine of 2 theta, well, that's going to be cosine of 2 theta multiplied by the derivative of the inside, which is going to be 2. So we have this for the numerator. Denominator, this here dropped the exponent forward, so that's going to be 4 sine theta multiplied by the derivative of the inside, which will make it cosine theta, and that's going to be negative, minus the derivative of sine, which is just going to be cosine theta, but carry the minus sign. And then derivative of negative 1, that's just 0, so this is our derivative. Nice. So let's see if we can now do a direct substitution. All right, let's see what happens when we do a direct substitution here. All right, so let's see what's happening. So as we start inserting, let's try to see if we can go with a direct substitution here. So as we start approaching pi halves, so we're going to go with sine of pi halves, and this is going to be from the left-hand side. So from the left-hand side, as we're approaching sine of pi halves, sine at pi halves is going to be 1. So that's going to be a negative value here, so it's going to be negative 1. All right. Minus 2 times cosine of 2 theta, and 2 theta, that's really going to be 2 times pi halves, so really just pi from the left hand side. So as we're approaching cosine of pi from the left hand side, this is going to give us a negative 1. There we are. divided by, and we can already see that the numerator is not 0, so that's really promising for us. That should be a numerator of 1. And denominator, so sine of theta and cosine theta, one of them has to be 0 because again we're going to be approaching pi halves, and that in itself is going to be cosine. Cosine at pi halves should be 0, which means it's going to 0 that first part, that first term in that denominator. But then minus cosine at pi halves once again. So cosine at pi halves again is just 0. So my denominator is 0, but my numerator is 1. And again, this is perfect scenario because now this is going to say this is going to go towards infinity. So it's no longer in indeterminate form, but we actually get a value for what's happening here. That value tells us that, hey, we have some vertical tangent and this is not a horizontal tangent. So what I want to do is I want to go back here and I want to modify this that we no longer have theta being equal to pi halves as one of our horizontal tangents. Alright, so let's go view this on GeoGebra and see what the heck is going on here. Alright, so come follow me. Alright, here I am on GeoGebra. I'm going to go to GeoGebra Classic. Once I'm here, I'm just going to modify the grid so that I can be in polar form. There we are. Alright, and I'm just going to start inputting my function. The function that I was working with was 1 minus sine theta, so that's what I'm going to work with here. Excuse me. So I'm going to start typing in, let's say r is equal to 1 minus sine, there we go, sine, and I need a theta, there we are, perfect, enter. There we are. Now let's zoom in just a little bit more. And just a little bit more. There we are. So again, we're looking at a cardioid here. Now we want to find out when do we have these horizontal tangents. Well, horizontal tangents, we said that there was only 3 of them happening. One of them was down here, and that was at 3 pi halves. That was awesome. One of them was somewhere up here, and that was the angle measurement of 5 pi 6, and the other measurement was here, which was at pi 6. Vertical tangents, we have a vertical tangent here, we have a vertical tangent here, and we also have a vertical tangent here. So we have 3 different vertical tangents, and in order to view this just a little bit more, I'm going to modify my distance for my angles here. Let's say pi halves. Alright, so I'm going to import this into GeoGebra, into the classroom whiteboard, and then I'm going to modify it there. That way we can see all of those horizontal tangents that we just found. Alright, so follow me along back to class and we'll go ahead and get that uploaded. Alright, so here we are. I imported this from GeoGebra, and I want to look at my horizontal tangents. So according to this rule, we have horizontal tangents appearing here and here. So there we have these horizontal tangents, but that horizontal tangent is occurring at pi 6, which was one of the angles that we got. The other angle was that 5 pi 6, which was here, and that was the 5 pi 6. So at those angle measurements, for the graph, we're able to get horizontal tangents. Same thing was happening down below over here. When I was looking at this value down here, well, that angle measurement down here, that angle measurement is 3 pi halves. And that was where we said that one of the horizontal tangents was taking place, right? We said 3 pi halves, pi 6, and 5 pi 6. And those are the angle measurements. This line right here is pi 6. This line here is an angle measurement of 5 pi 6, and this vertical line here is an angle measurement of 3 pi halves. Now, what about these vertical tangents? Well, vertical tangents, one of them was occurring at 7 pi 6, which is here. That's a vertical tangent. Another one is occurring at 11 pi over 6. That's there. And the last one was occurring at the pole. Remember, it's not the origin, it's the pole. So, let me make this one a little bit nicer. So as we start looking at these specific graphs and how to find their horizontal and their vertical tangents, again, the process is very, very similar to what we did back in Calc 1. The only difference here is that we are now just viewing this with, again, calculus and polar coordinates. So we must always rely on the methods that we've developed, and we must trust those methods. All right, so hopefully you all enjoyed this visualization of these polar coordinates and how to find their verticals and their tangent lines. And we'll continue polar coordinates in the next section. So I will see you then.